Hello, students. Let's get right to it, ladies and gentlemen. We have a lab activity to do today, and it is hot stuff. So let's begin with our lab activity on page 75 of your books. So if you haven't done so already, open your books to page 75. And the problem of the lab today states, how accurately can the specific heat of a metal be measured in the lab? You know what? I'm going to rephrase it a little bit. And we're going to say, let's rephrase that question and say, what is the specific heat of a metal? What is the specific heat of a metal? Can you determine the specific heat of a metal? Can you determine the specific heat of a metal? That's the question that we are going to be answering in the lab. And more than that, as I mentioned to you yesterday, we're making this a little mystery. And if we are able to calculate the specific heat of a metal, can you use the specific heat of that metal in order to identify an unknown hunk of metal? That's what you're going to try and do here today. So, as you write a hypothesis, I want you to again think of the question, can the specific heat of a metal be measured in the lab and be used to help you identify that metal? Take a moment and write your hypothesis. All right, hopefully you've got a good hypothesis written down. Hopefully you've got an idea of whether we're going to be able to do this or not together. And before we get to the actual procedures of the lab, I just want to take a few moments to explain the concept or the idea behind this lab to you. Because if you understand the big idea here, whether you're able to identify the metal or not by the end of the lab, it's okay as long as you got the big idea. So here it is. We are essentially going to be taking some cold water and putting into that cold water a hunk of hot metal. Now, I have some questions to ask you. You're going to put a hunk of hot metal into cold water. My first question is, what's going to happen to the cold water? My next question is, what's going to happen to the hot metal? Now, hopefully you said the cold water is going to warm up and the hot metal is going to cool down. But now, here's the deal. Here's the really cool thing about science and math. You see, the amount of, in fact, before I even show you the next slide, let me just remind you of some of the laws in science and nature. We mere mortals, cannot create or destroy matter, and we cannot create or destroy energy. We can only change its form from one form to another. So here's the deal. This is really cool, and we're going to use this principle in science to perform and complete this lab. The amount of heat energy that is lost by the metal has to be equal to the amount of heat energy gained by the water. We can put an equal sign here because we can't create or destroy energy. We can't create or destroy heat energy. It's got to go somewhere. So the heat energy from the hot metal is going to go to the cold water. But because we can't create or destroy, we can say they are equal to one another. So the amount of heat energy lost by the metal is equal to the amount of heat energy gained by the water. And again, because we can say they're equal to one another, we can start substituting things into this equation, heat equals heat loss equals heat gain, we can start substituting things into this equation to help us complete the lab. Do you remember what the equation for heat is? Look in your notes from yesterday. What is the equation for heat? If you said mass times delta T times specific heat, you are exactly right. So notice what I've done with our heat equation for our lab today. As we just got done saying, the heat lost by the metal is equal to the heat gained by the water. Well, I'm putting little subtitles here, some subscripts, I should say, corresponding to whether it's water, the W's in green, or the M's for metal in the red. So you might want to take a moment and think about this equation that I've developed here. The heat lost by the metal, we can substitute in the equation for heat, which is mass times delta T. And who remembers what delta T stands for? The difference in temperature, the temperature change. So mass times delta T times the specific heat of the metal will be equal to the mass times the delta T, or the change in temperature, times the specific heat of water. Now, if you think I'm going too fast, just pause the video and look at this and think about it for a moment. But then we'll move on, because the idea of this lab today is for us to solve for an unknown in this equation. And if you think about the problem, the idea is for us to solve or find the specific heat of the metal. And so before we even begin, let's do it mathematically so that we know what we need to be looking for. So mathematically, using a little bit of algebra, we can rewrite this equation solving for the specific heat of metal. So let's look. We've got an equal sign here, and we want to get the specific heat of the metal by itself. Now, don't be confused by all this other stuff written here. I know it may look scary to you, but think of it as if we were to say 2x equals 4. If 2x equals 4, what does x equal to? Well, you divide both sides by 2, and you've got x equals 4 divided by 2, which is 2. I'm sure all of you can do that, which means you can all do this. Because if we want to get specific heat of metal by itself, well, then we're just going to divide both sides by what's attached to it, what's being multiplied to it. And so if we divide both sides of the equation by the mass of the metal times delta T of the metal, this is what we get. The mass times the delta T of the metal cancel, and we're left with this equation. Again, if I went too fast, don't worry about it. You can replay it or just continue to follow along. The bottom line is this. The specific heat of the metal over on the other side, that's what we're looking for, is equal to the heat energy of the water, mass times the delta T times the specific heat of the water, divided by the mass of the metal times the temperature change of the metal. That's it. So if we can fill in all of these spaces, we can simply do the math to solve for the specific heat of the metal and see if we have done it right or not. So back to our lab page now. And I would like you to take a moment to copy this equation down on page 75 in that open space. And this, by the way, this same equation is written for you over on page, whoops, give me a moment here to turn the page. This equation is written in a similar form on page 78. But if you have it all on page 75, it'll make the time go a little bit quicker for you. So again, it's the specific heat of the metal equals mass of the water times delta T of the water times specific heat of the water, all divided by the mass of the metal times delta T of the metal. So if you need to pause me now, do so. Otherwise, let's continue. So here is our data table for our lab activity. We have a column of data we are going to collect for the water and a column of data we're going to collect for the metal. Now at this time, we're going to go to the close-up view in the lab. We're going to go through the steps and we're going to fill in the data as we go along. So here we go to the close-up view of our lab right now. And I'm hiding behind the pot, the hot pot. Woo, the hot pot. Okay. And by the way, just how hot is the pot? I'll show you how hot the pot is in a moment. But let's get to it as we are reading through our procedures. Step 1, get the materials, and here they are right before us now. Step 2, measure 100 milliliters of cool water and place it into the calorimeter. So I have in my graduated cylinder 100 milliliters of cool water, and here are my calorimeters. I'm simply going to pour the 100 milliliters of water into both calorimeters, returning the lids to them, and putting a thermometer into the top of the calorimeters and measuring the temperature. And the initial temperature of our water, and everybody can be writing this down right now, the initial temperature of your water is 20 degrees Celsius. 20 degrees Celsius. And by the way, hopefully by now I have divided you into two teams, Team A and Team B. If I haven't done that already, pause the video so I can tell you what team you are in. I have two calorimeters here because this will be Team A and this will be Team B, because we're going to be using two different hunks of hot metal here. And right now we are on step 3. We've determined the temperature of the cool water, and you have recorded that in your data. Step 4, record the specific heat of water in your data table. You should be able to do that on your own. Hint, hint. Okay. So now we are on step 5. And I'm putting the two hunks of metal in our boiling water. We've got boiling water here in the pot on the heat plate, hot plate. I'm just moving our calorimeters a little bit out of the way. Okay. And we're going to determine, let's see, we're going to complete this next step quickly, but before, yes, we're going to do this quickly. And I'm going to use heat gloves here because this pot is really hot. It's got boiling water in it. So let me tell you this. What do you think the temperature of the water is in degrees Celsius if it is boiling water? That will be the initial temperature of our hunk of metal, which is currently in the boiling water. And by the way, I'm just going to show you just how hot our boiling water is. It's as hot as this little rubber ducky would enjoy it. Okay, so here's the deal. In your data table, under the initial temperature of the metal, The metal chunks are in the boiling water right now. So what do you think the initial temperature of your hunk of metal is? Write it down in your data table now, and that goes for both Team A and for Team B. And now I'm going to take hunk of metal A. This is going to be the one that you're going to figure out, Team A. So Team A, I'm going to take this hunk of metal and quickly put it into the water in your calorimeter. Close your calorimeter up. We're going to put this off to the side so that we can measure the temperature change. And you should be looking, well, I'll be looking at that for you here in a moment. And now I'm going to do the same thing for Team B. Team B, here's the hunk of metal into the calorimeter for Team B. And I'm going to put that off to the side as I carefully move this hot plate out of the way. Bring our digital balance back. And here we have the calorimeter for Team A and the calorimeter for Team B. And now for a moment, we're going to go back to our notes, or rather to the PowerPoint, so that I can share with you some of the data, okay, that you have collected so far, as I am keeping an eye on the thermometers. So here is what you can write down. Let's begin with Team A. Team A. The initial temperature for Team A was 20 degrees Celsius. So you can write that down. Initial temperature for Team A, 20 degrees Celsius. The final temperature, which the temperature has balanced out now, I've just advanced some time here. Our final temperature for Team A is 29 degrees Celsius for the water. And by the way, that final temperature is also the final temperature of the metal, which is in the water. Now that the water has not, the temperature has balanced out, we've equalized the heat lost by the heat gained. So the final temperature for the metal is 29 degrees Celsius. Now, I've taken the liberty to dry off your hunk of metal and determine its mass for you so that you can write that down also. The mass of your hunk of metal is 60 grams. So Team A, 60 grams. This is your data so far, and what we're looking for is the specific heat of the metal, so we can put an X down for that. Now, let me just give some data to Team B. While Team A, you contemplate the empty spaces here for a moment. Team B, your initial temperature for the water was also 20 degrees, and your final temperature was 31 degrees Celsius, which consequently is also the final temperature of the metal. 31 degrees is also the final temperature of the metal. I also took the liberty of drying off your hunk of metal and determining its mass, and it turned out to be 180 grams, 180 grams. And the specific heat of your metal is also X at this time because that's what you are going to be solving. And as I advance to the next slide for Team A, I want you, Team B, to think about those empty spaces. So Team A, here's where I left you just a moment ago. And I'm curious, can any of you tell me, what do you think we could put in these empty spaces? Raise your hand if you could tell me what the mass of the water was. Remember, you got 100 milliliters of water. Now tell me, if you can, what is the change? Let's go down to the bottom one. Raise your hand if you know what the specific heat of water is. Hopefully you remember that from yesterday. And now raise your hand if you can tell me what the change in temperature of water is. And likewise, who can tell me what the change in temperature of the metal is? By the way, Team B, you can use this information also to help you. Think about it for a moment. So Team A, here's what we should have gotten. The mass of the water is 100 grams. It's the same as 100 milliliters. The initial temperature was 20. The final temperature, 29. The specific heat of the water is 1. And the temperature change was 9 for water. And over in the other column for Team A, we've got the mass was 60 grams, initial temperature 100, final temperature is 29, which means the change in temperature was 71, and the specific heat of the metal is X. That is our unknown. And now, before we get to the calculations, let's go to Team B and see if you got the appropriate numbers. Team B, let's see if you filled in your blanks correctly. Mass, 100 for the water. The change in temperature, you should have gotten 11. Specific heat of water is 1. The change in temperature for the metal, 69 degrees, and also X. And now for the remainder of our time, what I'd like you both to do, Team A and Team B, is this. Think about this data that you've collected and calculated so far. You're going to insert the correct numbers into this heat equation in order to try to calculate the specific heat of your metal. There is a right answer, and I would like you to read the note on page 75 after step 8 to see how close you came to the actual answer. And I'm going to give you time to determine your answer and see if you came up with the right identity for your metal. Again, Team A, this was your hunk of metal, a relatively light metal. Team B, this was your metal, a slightly heavier metal. And because of these two kinds of metals is what determines how or what has led some folks to make cooking pots with different kinds of metals on them because of the specific heat of different metals. So I hope that you achieve success with your calculations. Discuss what you think your team's metal is, and don't forget to study for tomorrow's quiz. So until then, I am going to say bye-bye.